Hi everyone, and welcome to this week's Oxford Discrete Maths and Probability Seminar. It's a great pleasure to start with a talk from Mihyun Kang, who's going to speak about Benjamini-Schramm local limits of sparse random planar graphs. Over to you, Mihyun.
Yeah. First of all, thank you very much for the kind invitation. I also thanked Alex, who will come back in about 10 minutes or so. So in this talk, as the title says, I will discuss so-called Benjamini-Schramm local limits of random graphs, not only that random planar graphs, but also other random graphs. And this talk is based on joint work with Michael Missethan, who is a second-year PhD student of mine at TU Graz. So in this talk, what kind of things we are interested in the following. Given a graph, you select one vertex, uniformly at random, and you ask, what does a random graph locally look like? I haven't defined what locally look like, but we will define it formally later. So the title of the talk hints what kind of local structure we are looking at, this so-called Benjamini-Schramm local limit. Anyway, what it does is that you select a vertex, you look at its neighbor and neighbors and neighbors and so on, as the picture just vaguely indicates. Second question that we have in mind is that how does a global structure such as the component structure, or how a component look like internal structure, affects its local limit or local structure? And the third thing is that what can we say about a local limit or local structure of a random graph if we would impose a global constraint to a random graph, such as being acyclic or being planar or being embeddable on a surface? Yeah? These kind of things we have in mind throughout the talk. Alex asked me to give very gentle introduction at the beginning, so it's a good time indeed to start from a very classical results on the Erdos-Rényi random graph. So to set the scene, let G be a graph chosen uniformly at random from the set of all vertex labeled and simple graphs on n vertices with m edges. Typically, the number of edges will depend on n. Yeah. And all the asymptotics in this talk will be taken as n tends to infinity. Sometimes we look at the limit object, but sometimes we do not look at the limit object. And we are often interested in the graph properties that would hold with high probability, meaning that with probability tending to 1 as n tends to infinity. But usually we have a very explicit probability, namely 1 minus big O over n to the minus third or something like that. But we always suppress in this fashion, yeah, with high probability. So one of the most interesting results of Erdos-Rényi already in late 50s and 60s were the following. You look at the random graph G and M, where the average degree, meaning that twice the number of edges divided by n, so-called average degree, converges to a constant C. And what they say is the following: if C is smaller than 1 in the so-called subcritical regime, then with high probability, every component will be small in the sense that they are of order at most log n, constant times log n. Furthermore, if you look at how they look, every component is acyclic or contains at most one cycle. So it's either tree or unicyclic, meaning containing one cycle. If you look at the picture on the left-hand side, there are trees and there are also two unicyclic components. Yeah, this is usually when C is smaller than 1, you will see only the picture on the left-hand side. I think I can use mouse indeed, like this. Yeah? This is how the subcritical random graph looks like with high probability. On the other hand, if average degree or the C, its limit is strictly larger than 1 in the so-called supercritical regime, then there is a unique largest component of linear order. We also sometimes call it giant component because this is larger than anything else, yeah, in the order. Furthermore, we know how it looks. It contains at least 2 cycles, like on the right-hand side, I see 1, 2, 3, at least, yeah, 5 and 6, and so on, many cycles. Sometimes we call them complex. And furthermore, it's not only containing at least 2 cycles, but also with high probability, it is not planar. Now, this is a classical result, but on the other, in terms of the order of the giant component, we can even say more using coupling with the Galton-Watson tree. Indeed. So let's throughout the talk, let L denote the largest component in a considered graph, and let rho be the positive solution of the equation 1 minus rho is equal to x of minus c times rho. If we work with the Galton-Watson tree, we will realize that this is just the survival probability of the Galton-Watson branching process with mean c, Poisson mean c. Yeah, so this famous equation, and rho is indeed corresponds to the proportion of the vertices lying in the largest component. So I just draw the picture, indeed not even using Maple, but by hand. I draw the picture how this the solution rho looks like. And you see that around when C is around 1, there is such a phase transition. And around when C tends to 1, much more study has been done first by Bolobash, Uchak, and among others. The so-called critical window and critical phenomena has been studied a lot. And this is about this classical result about the component structure. And let me return to my original question about the local structure or the local limit of the Erdos-Rényi random graph. When the average degree converges to a constant C, yeah, it is very well known that also it's very easy to see that you select a vertex R, uniformly random as the root, and you look at its neighbor. How many neighbors are there? We call it a degree. Degree of R is about Poisson C. Poisson C. Not only is R, if you select one neighbor of R, say U, and you look at also check how many new neighbors are there, new neighbors, so-called out degree, then it's also like Poisson with the mean C. And you select yet another vertex V, which is a neighbor of U, so neighbor of a neighbor of the root, then it's also asymptotically Poisson C, so long as we do not go too far away from the origin R. Well, you can repeat this kind of a heuristic, and also it can be made very rigorously. And this kind of an easy, simple observation can be cast in terms of the Benjamini-Schramm local limit. To be more precise, I need a little bit of a lot of definitions. The so-called local weak convergence is a very useful concept, which systematized by Benjamini-Schramm 20 years ago, as well as there is a big survey paper by Aldous-Steele, 2004. So a rooted graph is a pair of a graph H and a vertex R as the root of the graph. And we say two rooted graphs, H1, R1 and H2, R2 are isomorphic if there is an isomorphism from one graph to the other. But what is important thing is that because it's a rooted graph, we want to also send one root to the other. Yeah, the roots are preserved under this isomorphism. Then we say two random rooted graphs are isomorphic. So what is this picture is saying is this local structure. In order to quantify what we mean by local structure, we are using indeed given a rooted graph HR and a positive integer L, the ball of radius R of the rooted graph HR is the subgraph, induced subgraph of H. Yeah, it's so-called induced subgraph on the vertex set, so set of the vertices, whose distance to the root is n most R. In this picture, if you look, so like L equals 1, and this is just a ball. The induced graph consists of a root and the 4 vertices and the edges. If you take R equals 2, then this line, L equals 3, and so on. So for each such integer L, we can think of the ball of radius L. So it's induced meaning that the edges, if are there, they should be there. If they were not in the graph, they are not there. So induced subgraph of H on the vertex set in the ball of radius L. Yeah, given this notation now, I'm ready to discuss the local limit of the Erdos-Rényi random graph. So now, what do we mean by this Benjamini-Schramm local limit, or just simply local limit is the following. given two random rooted graphs. Now inputs are random rooted graphs, G1 R1 and G2 R2. Typically, the first graph G1 will depend on one parameter, say n. Yeah, so when we discuss about the Erdos-Rényi random graph, we had a parameter n and m, but number of edges m were also depending on n. So globally, it depends on n. Yeah, this is the context that we are heading for. So given two random graphs, rooted graphs G1 and G2, we say the local limit of G1 R1 is G2 R2. So let me suppress R1 at the roots. Yeah. So the local limit of G1 is G2 if for each fixed rooted graph H and a positive integer L, the probability that the ball of radius L of the rooted graph G1 is isomorphic to H and HR converges as n tends to infinity to the probability that the ball of radius, it's the same radius of the L of the graph G2 is isomorphic to H. Yeah, I depicted in the picture for each if constant L, what you see inside the ball should be the same. I indicated here, they are the same. I copy and paste. And the outside, they look a little bit different. But this is true for each L. So the picture indeed is not correct. But anyway, I try to do so that this gray vertices are in infinity. Yeah. But anyway, the graphs are, the picture has a limitation. So locally for any fixed ball, it should look like exactly the same as the other one. So we will use this notation, converges in distribution type of notation D. Yeah, so this is so-called local weak convergence by Benjamini-Schramm as well as Aldous-Steele. Now using this terminology, as I said, I am ready to describe the local limit of the Erdos-Rényi random graph. If the average degree, namely 2 times m over n, tends to a constant c, then the local limit of the Erdos-Rényi random graph is the Poisson-C Galton-Watson tree. So GWT of C is the Galton-Watson tree with offspring distribution Poisson-C, which is a rooted graph where number of children of each node is an independent Poisson random variable. Yeah? So if you have a question during my talk, please stop me and ask to make things clear. And it is perhaps worth recalling the dramatic change in terms of the component sizes in the Erdos-Rényi random graph, which happened when the average degree is around 1. So in terms of the global structure, let's say, or the component structure or internal structure, there were drastic change when C is smaller than 1 or larger than 1. But from the local limit point of view, independent of this number, what this number is, just local limit is Galton-Watson tree. Of course, depends only on the C, but nevertheless, universally Galton-Watson tree. So in this sense, Erdos-Rényi random graph, the local structure is perhaps not very much influenced by the global structure. It's a dangerous statement, but that's how I view the thing. Inspired by that, let us also look at another local limit of a well-known random structure named a uniform random tree. So let T be a tree chosen uniformly random from the all trees on n vertices. Namely, we impose a global constraint that a graph being acyclic and connected. Now we impose some global constraint. I do not want to see any cycle. I want to have them connected. Imposing that constraint, its local limit changes quite a lot. Namely, the local limit of the random rooted tree is then the so-called skeleton tree T infinity. Maybe some of you have seen this. This is also called the Caston tree, because some of the audience I see from the probability community, it's also called Caston tree of the Poisson type. So what is it? T infinity is a rooted tree obtained from a single infinite path, so path with one ray, where each vertex is replaced by an independent Poisson-1 tree, Galton-Watson tree, Poisson-1, Galton-Watson tree. This is Poisson-1, Galton-Watson tree, Poisson-1, Galton-Watson tree. Of course, sometimes I have vertices of the two children and so on, but what can I do? On average, yeah, it's average. I have one child. Sometimes you have two children and so on. This is the so-called skeleton tree to infinity. I see that there are some chats, but please go ahead. Huh? I cannot open the chat. Do I need to open it? If there are serious questions, please go ahead. Yeah, this is skeleton tree to infinity. And now, inspired by these two questions, during the last 20 years, I was working a lot on random planar graphs, and I was visiting Colin and as well as Christina and Alex, and I was wondering kind of local structure of a random structure that lies somehow between random tree and Erdos-Rényi random graph. Obvious candidate for me was a random planar graph. And so I asked myself, what is the local limit of a random planar graph? Let's say when the average degree converges to a constant C. Is it a Galton-Watson tree with a Poisson C, like in the Erdos-Rényi case? Or is it closer to the skeleton tree? It is closer to the random tree so that it is like a skeleton tree. Why this kind of question makes sense is also in terms of the global structure of a random planar graph. It has been known that it is known that some of the things are similar to like random tree or random forest, let's say, because we do not want to let them be connected, random forest, but some of the things are closer to Erdos-Rényi. So question is like this. So do you have any answer to that? If you haven't read my abstract, you might want to guess. What could be an answer? Is it Galton-Watson tree-like, skeleton tree-like, or something in between? Always clever answer is dependent on, perhaps depends on the C. Yeah, indeed. Indeed, in case of the random planar graph, the local limit depends a lot on the exact value, not exact value, how large the C is, the average degree is. And let me repeat, in case of the Erdos-Rényi random graph, when C is around 1, in terms of a global and internal structure, component structure, there is a drastic change. But nevertheless, local limit was always Galton-Watson tree C. Yeah? But here in random graph, we will see something perhaps interesting, at least to me. So to set the scene, let P be a uniform random planar graph on n vertices and m edges. And let us choose one vertex R, uniformly random from the vertex set of the graph P. So having said that, we have a random rooted planar graph. Then if the average degree tends to a constant C between 0 and 1, then the local limit of PR, the rooted planar graph, is Galton-Watson tree with Poisson offspring distribution with mean C. So Poisson C, Galton-Watson tree. Like in the Erdos-Rényi random graph, in the subcritical case, indeed, this result, indeed, we didn't show, we used the so-called the contiguous result of the subcritical Erdos-Rényi random graph is planar with probability 1, tending to 1. So indeed, we use it there. So I just recycle and copy and paste, and indeed it's true. Another end that is easy to show is when the average degree tends to 2. Average degree tends to 2. Yeah, on average, every vertex has 2 neighbors. Yeah, then the local limit over planar graph PR is the skeleton tree to infinity, but due to some other reason, indeed. Yeah, because typically when the average degree tends to 2, the picture looks like on the right-hand side together with the left-hand side. Indeed, the whole picture looks like. But if you select this vertex R uniformly random from the whole universe, then indeed it is very likely that this R will land in one of these subtree attached to. It's also far away from this kind of crowded areas. And the triangles are indeed indicating a large trees. Yeah? And also another thing that is very well known, indeed not by Missethan and myself, but due to my earlier result, is that in case of random phase transition of the random planar graph, that I have to say later. So indeed, it is in the consequence of a very interesting result on the largest component, namely, in case of the planar graph, when the average degree is around 2, something else is going on, namely, the largest component contains almost all vertices. Therefore, on the left-hand side, picture will be very much ignorable. Therefore, this root vertex R will be very likely to land in the largest, and furthermore, one of the largest tree. Therefore, it looks like locally, it looks like a skeleton tree. Yeah, this is the logic works. And when the average degree tends to in between, namely between 1 and 2, it is a linear combination of the two, as I was kind of suggesting. I do not want to read it, but let's read it, what it means indeed in terms of this local limit notation by Benjamini-Schramm. What it says is the following. For each rooted graph H and a positive integer L, we look at this probability that the ball of radius of R of the P is isomorphic to H converges to 2 minus C times the probability that the ball of the Galton-Watson tree of 1 is isomorphic to H plus C minus 1 times the probability that the ball of the skeleton tree is isomorphic to H as n tends to infinity. It's kind of a nice and linear combination of the two. And some of you might be already got idea why such a thing might be true, as the picture indicates indeed everything. So behind the scene, why such a thing is true is indeed heavily affected by the global structure and the component internal structure, let's say, how each component look. So in the rest of the talk, let me sketch proof ideas. Maybe I will end up being too quick, but hopefully not. As I said, the local structure of a random planar graph is significantly affected by its global structure. So let me just quickly wrap up what we know about the global structure, in particular about the phase transition in terms of the size of the largest component. As before, the context is that the average degree tends to a constant C between 1 and 6. When C is below 1, it was like with high probability Erdos-Rényi is planar, therefore nothing to discuss. Why this upper bound C is and most 6 is just due to the Euler's formula. You just plug in the Euler's formula. The maximum planar graph is the so-called triangulations. Triangulations have at most 3n minus 6 vertices, edges, right? Therefore, twice the number of edges divided by n tends to a constant between 0 and 6. Yeah, this upper limit 6 is not something strange. It comes from Euler. And what we have shown is the very interesting result together with the Thomas Ochak about 10 years ago is the following. If the average degree tends to a constant between 1 and 2, then the fraction of the vertices lying in the giant is just C minus 1. So average degree minus 1. It's just linear. In case of the Erdos-Rényi, there was this rho function, which was the solution of the transcendental equation arising from the Galton-Watson branching process, so long as the average degree is a constant. But this kind of a linearity works when C is between 1 and 2. And if C is between 2 and 6, so when the average degree is between 2 and 6, then the giant component contains nearly all the vertices, except little o of n vertices. This kind of strange linear curve in terms of the size of the largest. Any question? When I saw this for the first time, I thought that I proved something wrong. I was expecting more smooth. It's just linear. And as you see, another difference is in comparison to the Erdos-Rényi is that there are two critical periods when C is around 1. There is a typo C. I have to change. average degree used to be D, but then there was a convergence in D, so I wanted it to change. So everyone was indeed D, and then I changed, and then now I didn't change C. So C is around 1 and 2. Something interesting is going on there. And in case when C is around 1, we know exactly what should be the critical window, what happens in the giant component and other structure very well. In the sparse region, we know very well. It's different. It's really different from Erdos-Rényi, but nevertheless, it does have very interesting dynamics going on. But when C is around 2, still it's not well known from below and from above. Yeah. So anyway, this is one side remark about the global and component structure. Second of all, it doesn't help us too much. But C-1 is exactly coming from, this proportion of the vertices. There was the C-1 is exactly coming from that. So I will come back to that later. And now what is missing is the internal structure. So in order to look at the local structure, how locally looks like, of course, it might be helpful to look at the internally, how each component looks like. So to study that, I just copy this picture again. So L denote the largest component of a random planar graph depicted here on the right-hand side. And now we will introduce new notation S, being the small part. Namely, it's a graph obtained from the planar graph by deleting the largest. So namely on the left-hand side. So given a random, say, planar graph, when the average degree tends to 1 and 2, we know somehow there should be a largest component of linear order, which is not, which contains at least 2 cycles, and perhaps the rest. But this rest is not exactly the right picture because it's more than complicated than that, indeed. Anyway, we call it small part. And indeed, I think Colin McDermott, he also named the small part as the fragment. Yeah, so it has name fragment, but we call it as a small part. And the so-called core. The core is known also as the 2 core. What is it? It's a maximal subgraph of the largest component whose minimum degree is at least 2. So it's a maximal subgraph of the largest component, and each vertex has at least 2 neighbors. How can you get such a thing is the following. Given a graph, you delete every vertex of degree 1 recursively. So you delete one vertex, delete. Yeah, of degree 1 vertex by deleting the leaves first. The leaves are the vertices of degree 1. Recursively. And in the end, you will end up with all these green vertices lying here and perhaps isolated cycle or cycles. So indeed, the core can be obtained from a graph by deleting all the vertices of degree 1 recursively and deleting isolated cycles. And the core is, as I said, here depicted by green vertices together with the edges connecting them. Yeah, so on the right-hand side, it's a little bit small, but that's how it is. Yeah, so-called core. Furthermore, we can say more, something interesting is going on. It's just different from Erdos-Rényi is the following. The fragment, the small part, behaves like a critical Erdos-Rényi random graph. Critical meaning that the average degree tends to 1. This is really different behavior in comparison to the Erdos-Rényi. In case of the Erdos-Rényi, when the average degree is strictly larger than 1, if you delete the largest component from the Erdos-Rényi, what you see is the so-called subcritical Erdos-Rényi. Subcritical meaning that average degree is strictly smaller than 1. Yeah, on the other hand, for planar, it is critical. Furthermore, the largest component can be viewed as if it can be obtained from the core, namely this green thing, green vertices and instant edges, plus each vertex of the core vertex, the green vertex, each green vertex, namely each core vertex, is replaced by a rooted tree like that. Rooted tree, rooted at the core. Rooted tree, yeah? And furthermore, I didn't write it. furthermore, the total number of green vertices, namely the vertices in the core, is sublinear. So if you select one vertex uniformly random from the largest component, it's very likely that that random vertex lies in one of those three components rather than the core vertex. Yeah? Therefore, this leads to a study on the special type of a forest consisting of rooted trees. Do you have any questions so far? Yeah, so I delete this green part. Then what is left is the following collections of rooted trees. Yeah, this square vertex is representing the core vertex. Yeah? To study such a random forest, we can do it indeed in general. Let F be a uniform random forest on n vertices with exactly t many tree components. Yeah, like here. 1, 2, t many tree components and rooted.
Ian, may I just interrupt? There's a question from the chat. Can there be more than one core?
Yes, yes. Oh, more than one core. You mean that the core is disconnected?
I assume that's the meaning of it.
Yes, yes. So it can be indeed. It's also in case of the Erdos-Rényi random graph, the core is with high probability connected. But on the other hand, if you look at the two core of a random planar graph on that regime, when the average degree is between 1 and 2, indeed, core is not necessarily connected with high probability. With some probability, there are very small complex components around, you know. It's not connected, that's the main point. There is a huge difference between the two core of the Erdos-Rényi or two core of the planar graph. Therefore, it's indeed a very interesting thing. And if you look at the two core, indeed, that in case of the Erdos-Rényi, it is very well known that the core emerges together with a giant, just so called. But only the three core appears suddenly. But two core of the planar graph does not appear together with a giant suddenly, but when the average degree is around 2, so it appears much later, linear size core. So something else is going on anyway. So thank you for the question. In case of planar graph, the two core is not connected, not necessarily connected with the high probability.
But just to confirm, your C is the core of the largest component.
Core of the largest component, but you can also relax your definition a little bit. You can there are also other concepts of two core, namely you do not you know, it might be that there might be two complex components, yeah, of cycle, like a figure 8 and the subdivision of it. It might be there in case of the planar graph. Of course, my drawing is a little bit typical, so it's a little bit misguiding, but anyway, that's how it is, right? I have to convince you that it works. Yeah, indeed, a lot of, behind the scene, there's a lot of technical calculations going on. I'm swapping every technical details under the carpet. Yeah, anyway, so these are the things after deleting all these tree components, unicyclic components, and the core. So this is the trees, forests that are relevant. And if you select one vertex RF uniformly random from the vertex set of the whole forest, if you look at the forest, indeed, there will be also giant forest, giant tree component. This is yet another topic, but anyway, there will be a giant tree, and it is very likely that it lands in one of such big tree. And if you look at its local ball, any ball of radius of any given L, then local limit of T and RF, here is written TF, yeah, this tree locally, is the skeleton tree, as we have seen by Grimet's result. On the other hand, if you look at the forest level, as I told you, forest level, then this RF will land in one of the largest tree, and therefore local limit, locally, I do not see the whole picture, right? Locally, indeed, the forest local limit is also the skeleton tree to infinity. Another thing that is very important and relevant to us is that because these black square vertices are the core vertices in the original graph. So if you select RF uniformly random from the whole vertex set, then it's very likely the distance between this RF, the root of the forest, is quite far away from the root of the tree that is contained in it. The distance between RF, RT and RF will be very large. So if you look at any ball of constant radius, you will not be able to see that RF, which means the core vertex, you will not see it. This is indeed a very important technical detail, but anyway, nevertheless, it's not very difficult to prove, but you have to say it. Having now said that, now we can cook up something in the level of the largest component. As before this, all these notations are recycling. So recap, L was the largest component, average degree is between 1 and 2, and we know that the proportion of the vertices in the largest is C-1. And now we should be careful how we select the root. Now we constrain ourselves that RL will be chosen uniformly random only from the vertices in the largest component. Yeah? I restrict myself, I will select my root only within the largest component. Then due to the fact that the core is quite small, this RL is very likely to land in the forest, and very likely that it's land in the largest tree, and that vertex will be very much far away from the core vertex. Therefore, locally, it looks like a skeleton tree. On the other hand, similar reasoning. Now I look at the small part, and we select the vertex, root vertex, being selected outside of the giant, namely within the small part. Then we already saw that the small part behaves like a critical Erdos-Rényi random graph, and critical meaning that the average degree tends to 1. From the earlier result, we know that critical Erdos-Rényi random graph locally looks like a Poisson 1 Galton-Watson tree. Yeah, so if you restrict ourselves that, oh yeah, the root is selected there, then Poisson 1 Galton-Watson tree. If we restrict ourselves, the root should be within this giant component or largest, then it is skeleton tree. Now we can relax ourselves, namely returning to the original question, namely if we select the root uniformly random from the whole universe, then with the probability 2 minus C, it will land outside the giant. With the probability C-1, it lands in the largest component, and therefore this combination. Relatively easy looking. And indeed, we can say even more about the local limit of the two core. Namely, I restrict myself to be the core. So maximal subgraph of the largest component P with minimum degree at least 2. Yeah. The question that somebody was asking whether the two core can consist of more components, then we don't restrict ourselves to the largest component here. Yeah, it can be also maximal subgraph of the whole graph with a minimum degree at least 2. This is a usual definition of the two core. And in different contexts like coloring problems and so on, then you can have more, but we restrict ourselves to be the largest one. So anyway, C. And we select one vertex uniformly at random from the vertices in the core only, then indeed the local limit of the core is also a skeleton tree, but with 2 rays. Yeah? T infinity of 2, meaning that there are 2 infinite paths sharing one common root, and each vertex of the path is replaced by a Poisson 1 Galton-Watson tree. So I have sometimes too many children, but that doesn't matter, on average 1, yeah? So each vertex of the path is replaced by Poisson 1 Galton-Watson tree. Yeah? But we have 2 such infinite paths or rays. And indeed, locally, the core looks like that, as depicted here. Using this kind of notation, we can say even local limit of the planar graph using this terminology, namely introduce T infinity of K being a rooted tree obtained from K infinite paths rooted at one common vertex. And we have a K rays, and each vertex of the path is replaced by an independent Poisson 1 Galton-Watson tree. Now you have K of such rays. And we will write also at least K if it consists of at least K infinite path. Yeah, so can imagine that. Then using this T infinity of K notation, the local limit of a planar graph can be written as indeed 2 minus C times T infinity of 0. Namely, there was no infinite path. Therefore, it's a Galton-Watson tree with Poisson mean 1. So Galton, yeah, Poisson 1 Galton-Watson tree plus a C minus 1 of T infinity of 1 infinite path. Using this terminology, you can imagine that there is a purpose doing this later. So do you have any questions? I think this is it about the results. If you don't have question, I will just summarize our results and put, I think, one open conjecture. I think conjecture. No?
That's great. There aren't any questions in the chat at the moment. So.
Maybe I have a question. I think you had C in the open interval 1, 2, but you said the result at the beginning for C equals 2 as well. Is something a bit different happening at C equals 2, or is it? C
equals 2, I think C equals 2. I think I have something in the summary. Let's return to that. This is Paul, right? Paul Ballista, right? You're asking.
It's Oliver.
Oliver, sorry. It's Oliver. So let's return to that later. Yeah, sorry, the voice was very, very much to our old friends. So if Paul's consider me as a friend as well. I consider you as a friend. Yeah, I think that point I will return to later because it's a very important point indeed. In case of the Erdos-Rényi, when C is around 1 is important. For me, kind of nobody can solve anything around when C is equal to 2. Why saying it is the following. So in my case, I use so-called probabilistic counting. I start from something, internal structure. I build up the core, I build up the forest so that I can count planar graphs very well under the condition that it's sparse, when C is like below 2 or around-ish. But there is yet another community, the so-called analytic combinatorics community. They use the bivariate generating function to count the planar trees. And there, the restriction is that the average degree tends to a constant, but this constant is strictly larger than 2 and strictly smaller than 6. You know, there is this gap when C tends to 2. So C tends to 2, I prefer to return later. Yeah. In the summary, I have that item. So let me wrap up, yeah, conclude my talk with some summaries and open problems. So maybe I want to inspire also what kind of open problems are there. Just wrap up. We have seen the so-called famous phase transition and critical phenomenon in uniform random graph as well as in random planar graph, just to look at the fraction of the vertices lying in the largest component behaves like that. This is exactly this following the survival probability of the Galton-Watson tree. It's irrelevant what value C is, so long as C is larger than 1. Yeah, if C is a constant, it behaves like that. On the other hand, for planar graph, below 1 is the same as Erdos-Rényi. Yeah? Between 1 and 2, there is a linear combination, a linear size. So the fraction of the vertices in the largest is just average degree minus 1. And above 2, almost all the vertices lying here, but around 2, mysterious things are going on. Here we know very well. Yes, it's amazingly well, but here no. Furthermore, important thing around 1, yeah, so I have to also touch around 1 once more, is the distinction between Erdos-Rényi case and planar case is the following. The fragment, the small part obtained from the Erdos-Rényi after deleting the largest behaves like a subcritical Erdos-Rényi, subcritical here, subcritical Erdos-Rényi random graph, namely the average degree is strictly smaller than 1. On the other hand, in case of the planar graph, the fragment, the small part, namely the graph that is obtained by deleting the largest component behaves like a critical Erdos-Rényi random graph. I think critical random graphs are the specialty of Christina, no? Critical Erdos-Rényi random graph when the average degree tends to 1, and there we know a lot of things. And we know a lot of things, but we don't know a lot of things in case of planar graph as well. Yeah. So anyway, this is the distinction. So in case of the Erdos-Rényi, this is so-called symmetry phenomenon or symmetry rule. But in case of planar graph, it doesn't have such a very nice symmetry phenomenon. Mysterious field. So when average degree tends to 1, something else is going on in case of planar graph. Furthermore, these kind of results that you are showing about the planar graph indeed also can be extended to any graphs embeddable on an orientable surface of constant genus. Indeed. Local limit, global structure, whatever. If you have a fixed constant genus, then any graph embeddable on a orientable surface of genus G, similar things happening. And we have seen that the local limit of a local limit of a random planar graph when the average degree is between 1 and 2, we have seen this combination. And now I'm returning to the question of the Oliver. In the second critical regime, when the average degree tends to 2, we said that the local limit of the random planar graph is the skeleton tree to infinity. The reason is that when in this regime, when the average degree tends to 2, the giant component is of order n plus little o of n. It depends indeed the speed, how fast this converges to 2. If it fast really quickly, yeah, very near to 2, it depends on the critical window, then indeed the size of the giant is indeed n plus big O of 1. Even you can go in that regime, yeah, but it really depends on the critical. So there is indeed a second critical phase here in the critical window being of size strangely n to the 3/5, whatever happening outside the giant, but it's too much detail. Yeah, I think this is a question. And furthermore, more important thing is that when the average degree tends to 2, the number of vertices in the core is still sublinear. Therefore, if you select R, uniformly random from the total universe here, then it's very likely that it will land not in the core, but on a vertex on the forest, furthermore in a giant component of a tree. Therefore, locally, it looks like a skeleton tree. Have I answered your question, Oliver?
Yeah. Thanks.
Yeah, and now comes, if you have seen my slide earlier, because I sent the earlier version to Christina, I realized that my conjecture is either wrong or too brave. And now another thing before I go, yeah, open problem is that indeed in our theorem, because it heavily depends on my result with the earlier result, indeed it's not quite true. We have a restriction that m is at most n plus little of this little bit of this correcting term. It's really depend on the method that I'm using. I use the so-called core kernel method introduced by Balabolobash in early 80s. Kernel, I will return to that later. Yeah, it's so-called kernel core method, very classical method. Nevertheless, for sparse random planar graph, it works perfectly fine. But drawback of this kernel core method is that when m is larger or around n, it's not quite correct. There are too many error terms occurring. So it's the drawback of the method. I told you already, another drawback of another method that is so-called analytic combinatorics using bivariate generating function, namely the setter point method or the singularity analysis, is that they can do only when m is some constant times n, where that constant is strictly larger than 2. So there is this gap, yeah, from the both method. And it is kind of an area where we don't know well, yeah? Even the speed, how the structure, the crowded structure works. Nevertheless, in terms of the giant component, we know that the number of vertices in the giant component is like n plus little of 1, but on the other hand, the other things are going on, so like core and so on. Another thing, the brave conjecture is the following. You look at also the kernel. Kernel meaning that this blue vertex. What is it? Look at the core and you replace the path whose internal vertices have the degree 2. So if you delete this tree component, I mean the vertices of degree 1 recursively, then in the end we are deleting the trees dangling. And if you delete them, you end up with this nice picture, and then something like this path. Yeah, it's a subdivision of a kernel indeed. If you replace such a path whose internal degree is of degree 2 by an edge, and you obtain the so-called kernel. So you obtain the 2 core from the kernel by subdividing the edges indeed, yeah, the other way. So kernel is this blue thing. So this is brave conjecture. So from my earlier calculation about the size of the core, size of the kernel, it suggests the following conjecture, namely, there is the so-called critical value TC, which should be strictly larger than 2. And somebody may ask this one, I do not want to say something like 4.42, very strange number, concrete number. The strange is that it is concrete. It's not 4 or 5, it's 4.42, but there is a reason why. Anyway, there is a critical value TC, which is strictly larger than 2, but I believe it should be really strictly smaller than 4.42. And to value A and B, which is between 0 and 1. And the average degree converges to some constant between 2 and TC, this critical value. There is such a TC so that the number of core vertices, the total green thing, yeah, this blue is green and blue, yeah. Total number of green vertices is like A plus B times n asymptotically. And the number of blue vertices, the so-called vertices in the kernel, is asymptotically B times n. Furthermore, using that, we can also obtain the local limit of PR, namely the fraction of the vertices lying not in the core is exactly 1 minus A minus B. Then it looks like the root will land there with probably 1 minus A minus B, and then local limit is the skeleton tree of 1, yeah, having just one infinite path. And if root lands in this purely green vertex, namely core, but not in the kernel, the fraction is A, then it will be like skeleton tree to infinity of 2. So we have 2 infinite paths, 2 rays. On the other hand, if lands in the blue-green vertex, blue vertex, the fraction is B, but then it's T infinity of at least 3. So my brave conjecture was indeed 3, because in a sparse regime, it's very likely that kernel is also cubic. It does have only 3 neighbors, but on the other not, I'm going far away, further. So I cannot guarantee what is the typical average degree is. So I wanted to make it 3 and 6, but then I gave up. So anyway, I just bravely made it, but this at least the 3 should be fine-tuned. It's not well done. So this is my conjecture. And this concludes my talk, and thank you very much for your attention and questions.
Thank you very much, Mihyun. Perhaps I can kick off with a question before I invite other people. So is anything known about the degree distribution of the kernel vertices in this regime? I guess that's what you would need to replace the greater than or equal to 3 here.
For planar graph, yes and no, but as I told you, the degree distributions or the maximum degree type of things are well known, of course, for Erdos-Rényi, in particular GNP model. Yeah. On the other hand, for planar graph, it's not. There are a lot of studies in case of the so-called N vertex model. This is also a specialty of Colin, as well as the people in Vienna and Barcelona using this so-called N vertex model. Namely, you look at the uniform random planar graph on N vertices, but you do not specify the number of edges. Then you can show indeed the number of edges in that N vertex model is around 2.21 times N. And it does have a normal distribution. Therefore, I have this famous number 4.42 because average degree is in twice, right? Mm. Exactly this conjecture, 4.42 comes from this expectation of the number of edges, which means in the majority of the planar graph, a typical N vertex planar graph is dominated by the behavior of the very dense regime when the average degree is like around 4.42. And then they can discuss the maximum degree distribution or sometimes degree distributions using the generating function or Boltzmann sampler, but not in the regime that I'm interested in, namely here. I'm interested in around here, but a little bit larger, but not closer to here. Second thing, what some of you might know, because I've seen some of the people who are working in this kind of area, is that there is a so-called uniform infinite planar graph as a limit, as a local limit of N vertex planar graph indeed by Benedict Stiefler. There is a very nice result by Stephenson and so on. There are many people working, but most of the people are working on the so-called N vertex model. And also maps, the graphs that are embedded. Same. They only fix the parameter number of edges, but not both. Yeah. So in my case, I'm inspired more by the Erdos-Rényi type. So I always look at the number of vertices and edges and their interactions. And I told you, if you want to have a very challenging open question, I think this area. It's like, but you have to open up the window as well, the behavior. And also I have a conjecture about the chromatic number threshold behavior of the either 4 or 3. Also, it happens to be the n plus, like number of edges around n plus n to the 7/9 or something strange conjectures around always when the average degree tends to 2. Interesting, for me at least.
Thank you. Does anybody else have any other questions?
Feel
free to unmute yourselves if you'd like.
I had one question. Could you go back to the slide where you got this convex combination for the limit?
Here.
Oh, there was even one earlier, wasn't there? Okay, but okay, that
because
I thought there was one
it is
earlier.
indeed a combination.
So maybe it's this one. Yeah, this one. So maybe this, you've said stuff that immediately answers this question. But anyway, what I was wondering is if you pick, so you pick P at random, then you pick the random point, then you have a certain probability that it looks locally like GWT or T infinity.
Right.
Now, if I pick P at random and then pick 2 different random points independently, you would guess that locally around those points, whether it looks like this guy or this guy, should be asymptotically independent as things go to infinity.
I
Is
guess
that
so.
obvious, true, maybe, or?
Not obvious, but I believe that it's very likely that they will be far away. Therefore, there will be 2 independent copies of whatever, either lens there. Yeah. So I cannot say, but I think your intuition should be correct, to be honest.
Okay, thank you.
Even perhaps for any alpha moment, if kth moment when k is constant, they will be independent rather. But on the other hand, I shouldn't be too brave because in case of planar graph, because of this constraint, well, any graph on a surface is the following. If you can view this, it's not correct because it's not uniform, but you can view as if the edges come and you can add them if it stays planar. Yeah. So dynamical model does not give a uniform model, but on the other hand, you can think. But each time you want to add one extra edge because of the planarity, this richer cannot get richer like Erdos-Rényi because of the planarity. It will spread more evenly over the components. So as I said, due to this planarity constraint, it's the same as being a genus constant. There are this interaction between the largest and planarity and then outside. It's not always the richest get richer like in Erdos-Rényi, but it's more social in terms of the distribution of the edges over components.
Thank you.
Welcome.
Anyone else? Okay, let's go ahead.
So if the average degree is some constant larger than 2, can you prove Benjamini-Schramm convergence?
I don't think it's a known, but I told you that because of thanks to the result by Benedict Stuffler about n vertex model. So when the average degree is around 4, let's say 4, yeah, this famous number, because of the typical random n vertex model.
Yes, but let's fix some number other than that.
Other than that, I don't know. It's a big open problem. It's one of my challenging open problem that I want to put in my grant. If I have to apply for a grant, really, I have thought about it. To be honest, I have to think a lot more.
Thanks.
Yeah. Actually, the conjecture that you have on the screen looks a little bit implausible to me somehow. Because
I told you, I
it's a
met
very
this
interesting
conjecture
question.
this morning.
What it is?
Huh?
Okay, because in the local limit you somehow see the skeleton, and so in this case, if you've got the core and the kernel are of comparable size, so if you're in the core, you're sort of not very far from the kernel. And that should, as you explore out, if you remove all the tree bits, you see something that doesn't just stay as 2 paths, but starts branching later on. And I think that sort of survives the local limit. So the local limit will be, if you're in the core but not the kernel, then it should look like some other thing. But maybe there's just sort of slight modification that it's, it's some branching process where you have degree 2 and you have the branching process corresponding to the core or the kernel, which is
yes,
with minimum offspring between 1, something like that.
So instead of a skeletal trees like that. So as I told you, this conjecture is this morning. I was thinking, and then maybe this kind of obvious kind of conjecture can be made. But my initial conjecture was indeed like a simpler branching process. Maybe it's simpler. If you look at it, I mean, what I'm saying is the T infinity of at least 2, right? Isn't it kind of a? Yeah, I should be a little bit more clever than this. As I told you, I was too quick in making this conjecture. I think I will give a slide to Christina to update the slide on homepage, but I think I will make you a question mark rather than making this brave conjecture. Even one conjecture. Yeah, maybe, Oliver, you're right. To be honest, I don't know, because initially, even this, the two core limit, you know, at the beginning, it wasn't, to me, to be honest, a surprise. Of course, you shouldn't be too much surprised, because of it's very likely that the core vertex, not the blue ones, it's very likely that it will be on the subdivision of the edges of the kernel. So you can imagine that, yeah, indeed, locally I see only these 2 passes, and then this Galton-Watson tree of Poisson 1. But why Poisson 1? Because the average degree is like between 1 and 2, you know, kind of imagination. But we are behind that. So to be honest, I don't know. Maybe next morning I make another conjecture, Oliver. Maybe you have the right conjecture. This morning I came up with it. Yesterday was something different. But I think this first line is indeed based on something that I computed already. When TC is strictly larger than C, but I don't know this upper bound. That's why I put this very strange threshold. So it can't be true for every, but I know that it's from some point when the average degree is strictly larger than 1, I see these green vertices will be linearly many, and the kernel vertices will be also linearly many. And at some point, the kernel vertices are all degree of 3, but then at some point, there will be other degree distributions, and that's what Christina asked. Whether do we know anything about this degree distribution? I don't know, unfortunately. Maybe you guys can do that. But Oliver, on the other hand, it can't be just a Galton-Watson branching process, because you have to subject on being planar, right? But locally, how much is it influenced?
Maybe it's some strange mixture, that there's a Poisson process with always at least 1 offspring, giving you the sort of branching skeleton tree, and then on that you've got Galton-Watson 1 trees, which is different from a single Poisson. Maybe I don't know.
That seems like a good place to stop, with plenty of food for thought. I'm going to stop recording.